Let me begin. So what I will do today is to review in some more detail the construction of this omega piece, because those will essentially play a central role in eventually formulating the measure on superstring theory. Okay, and in fact this is not related to off-shell, even on-shell amplitudes in superstring theory will require making use of this omega piece. So we again try to review, and I will give you different ways of thinking of omega p. So first, we introduce specific coordinate system on PGN, because so far I have been defining omega p in abstract term in terms of its contraction with some tangent vectors. Okay, but perhaps it's more familiar to think of omega p in terms of its components, right? You normally write a p form as omega I1 to ip dxi1 to dxip. Okay, so let's try to see how what I have described so far can be reformulated in that language. Okay. So the first step is to introduce coordinates. Which are denoted by x's on PGN. Okay. So there are of course infinite number of coordinates, because PGN is an infinite dimensional space. Okay, so there will be infinite number of coordinates on this space PGN. Okay. So let me be more specific about what we mean by introducing coordinates on PGN. Okay. So as we have discussed, we can take a general genus Riemann surface, divide it up into three punctured spheres and disks around the punctures. So if we consider the spheres Si, okay, we introduce coordinates Zi on the spheres, and on the disks, if we call this d1 and d2, okay, on the disks we introduce coordinates Wa, and then you specify the transition function Zi equal to Fij of Zj and Zi equal to Fia of Wa on the overlaps. But now we will be more specific. Okay. So when I say Fij of Zj, these Fij, okay, which are the transition functions, are parameterized by coordinates on PGN. Okay. Different points in PGN will correspond to different transition functions. Okay. So you can think of these Fij's as functions of Zj as well as all the x's. Okay. Similarly, these we can think of as functions of W and all the x's. Okay. So let's be even more specific. Okay. Let's try to see how you can explicitly think of these x's. Okay. So once I discuss that at least locally we can choose parameters, okay, such that there is one gluing parameter from each of these overlaps, one complex gluing parameter, because they are altogether 3g minus 3 plus n circles. Okay. So on each circle, if you have one complex parameter that labels the corresponding transition function, we have 3g minus 3 plus n parameters, complex parameters, right? So twice of that is 6g minus 6 plus 2n. That's the correct number of dimensions of NGN. Okay. But for PGN, of course, we need more parameters, okay, because you have to label the fiber, and that you can do by choosing arbitrary functions across these overlaps. Okay, because for each disk we have arbitrary function. Okay, so let's be more specific. Okay, so take each SI Yes.
So I already have these coordinates, right? Zeta is the back to the x's.
No, zeta is are the coordinates on Riemann surface.
Okay.
X's are coordinates on p plane, which are quite different objects.
So you are taking these functions in terms of both or?
Yeah. So zeta is a function of zj, but what function it is depends on the x's. Right? Because, for example, if you take z1, z2 equal to q, right? Z1 is a function of z2.
This q will be
The q will be like the x. Is that clear?
So it's like at any given point x's, I
Yes.
can set up various kinds of coordinates.
Yeah. But let's suppose that you have to, but the various kinds of coordinates will not make a difference, right? Because reparameterization, as you have seen, doesn't move in PGN, right? Unless it's reparameterized from the W's. Okay. So forget about setting up different kinds of coordinates. You fix some coordinate in the system, right? But in that coordinate system, when you make this, when you change x, that means you are changing the transition function. Okay. So let's try to be very specific. So take each SI to be complex plane with holes around 3 fixed points. Say let's call this one equivalent. Okay, these are fixed. Okay, we are not going to change them. Okay, it could be 0, 1, 2, for example. Okay, so take each complex SI to be in complex plane around with holes cut out around this. So each SI has 3 holes, right? You can think of this as a complex plane with point at infinity, of course, is identified. And then you can take the relation that Zi minus M, okay, on the overlap circle. Zi minus M, okay, let's call it C alpha, on overlap circle C alpha, Zi minus M times Zj minus An equal to, what do they call it, Q alpha. So Q alpha parameterizes the relationship between Zi and Zj. Okay. So Q alpha will be one of the x's. Right? Because as you change Q, you are changing the transition function. It's called A1, A2, A3, and so what are these A and N? These are one of these A1, A2, A3, right? Depends on which one of the circles of this sphere is grouped to another circle of the sphere. Right? So which particular circle you have taken is of course a convention dependent thing, but we can choose, we can make fixed assignments. This is 1, 2, 3 for the first circle, right? 1, 2, 3 for the second circle. 1, 2, 3 for this one. 1, 2, 3 for this one, and so on. Yeah? Then it becomes clear what is what. For example, when you consider this overlap, it will be Z1 minus A3 is equal to Q times, or Z1 minus A3 times Z2 minus A2 is equal to Q1. Okay? Because from this side, this circle is like a whole cut out around A2. That's what I mean by this is the 2. Okay? And from this side, this circle is like a whole cut out around 3. That's why I am calling it A3. So is this clear? Right? These are just 0, 1 and 2. Right? These are not changing, but the Q's are changing. Right? So this introduces altogether 3g minus 3 plus n complex parameters. Okay? And those are sufficient to parameterize MGN. Okay? If you are only interested in MGN, that's the correct number. Okay? And except for strange cases, it gives a faithful representation of the moduli space. Okay? Only in very special cases you may find that by varying this, you have to reparameterize the z's. Okay? But generally it will not happen. But you also need coordinates on a fiber. Right? So those again can be introduced in the following. On overlap circles. These are parameters. Okay, we just postulate some arbitrary relation between zi minus am and the w's. But these are totally arbitrary. By changing these p's, you don't shift the position wa equal to 0. Wa equal to 0 is a special point where the function is. Okay, so in this z coordinate system, the function is at zi equal to n. Zi equal to n. So these are also coordinates on PGN, but these are the coordinates on the fiber.
Sorry, that is equal to Wn?
Yeah, zi minus m equal to, so this is a transition function. So this is Fij, this is giving Fij, and this is giving the small Fij. So in this notation, Xs is a collection of Q alpha and P an. Okay, so this is one way you introduce coordinate system on PGN. Right? In this parameterization, we can think of this as a coordinate on the base and this as a coordinate on the fiber. Right? If you keep this fixed and change PAN, okay, you move on the fiber. Right? Because this you can undo by reparameterizing W's. Right? You can, because W goes to this is a perfectly well defined transformation on the disk. Is this clear? Okay, so this introduces coordinates on PGN. Okay, now let's expect how to define forms, okay, how to construct the omega p's.
What is the subscript on Zi minus A? What is that?
Zi minus AM. This one?
Yes, yes. AM.
Oh, this is again this particular hole here, right?
Yeah.
I have taken this to be hole number 1.
Yeah.
So it will be Zi minus A1 being given by related to W1 in that fashion. Right?
Yeah.
That A1, A2, A3 is just which hole you are doing. Right? Which hole is being included. Depending on that, you pick Zi minus A1, A2 or A3. Okay, this assignment you can fix once and for all. It's a convention. It's just a convention. You just fix once and for all as 1, 2, 3, 1, 2, 3 and so on. Okay. So locally by using these parameters you can span PGN. Okay, it may not give a global coordinate system, okay, but it's perfectly good as a local coordinate system. Okay. And with that you can now define the form.
So you could introduce this PN as the coordinates to the PGN since this n running to infinity gives me this infinity.
Exactly. So this makes it clear that fiber is infinite dimensional. The base is finite dimensional because there are only 6g minus 6 plus 2 n real parameters. Right. And this one is infinite dimensional. Right? That's the infinite dimensional fiber.
But how do we know that this infinity is countable?
Well, you are parameterizing an arbitrary analytic function, right, by this expansion.
Okay.
Right? And as I said, this is not a global cover. Okay? If the PANs are sufficiently large, right, then this may develop a singularity inside the disk. Right? Then it's sort of no longer an IO transition function. Okay? So you use this to define the transition function in certain domains. Okay? Then beyond that, you have to change your W coordinate system. Okay? You use or you change your Z coordinate system so that you can again define a new way of specifying transition functions, which can be parameterized by this infinite number of parameters. Okay, so because it is a conformal transformation, analytic transformation, that you use the usual parts in the expansion, okay, which is valid at least within certain range.
Could you have allowed fractional positive parts of omega A?
No, because that's not allowed, because this is not a well-defined transformation on W equal to 0.
No, yeah.
Right? So those kinds of transformations, well, you can do it, but they will be redundant in the sense that if you make it fractional part, right, that actually changes the MGN, that moves you in the MGN, because that you cannot undo by reparameterizing W. See, you can put, well, fractional part perhaps is is not allowed because it's not even single valued around the disk, right? At least it should be single valued around this. It should be one-to-one transformation. But what you can do is that you can use WS. Okay, you can use functions which have singularities inside the disk. Yeah, that's a perfectly good description of transition functions. It's just a different parameters, and if those kinds of functions, right, if you use those kinds of functions, and if you change parameters inside those functions, they are actually moving in edges. Because those transformations cannot be undone just by reparameters in W, right? So this way of parameterizing, right, makes it clear what are coordinates on the fiber and what are coordinates on the base. Right? These are the coordinates on the fiber because these kinds of transformations can be undone by reparameters in W. Right? But you are certainly allowed to use other functions here. Right? That just as you are allowed to use other functions here. Right? I mean, nobody tells us that it has to be like this. Right? It can be a complicated transformation. I am just giving one example, right, by which you can introduce these coordinates on PGN. Right? But any other parameterization is also fine. Right? This is referred to a parameterizing PGN. The given space can be parameterized in many different ways, right? There are different ways of introducing coordinates on PGN. Is this clear? Okay, so now I want to keep this. Maybe I don't need to keep this. You can stop that board. Yeah, that's what I can stop this board, right?
Yeah.
It will just go
Because
up.
anyway to come.
Okay. So now I want to introduce this vector field. Vector field VS. So let's call it VS, and that's what the argument is. Yeah? On sigma here associated with del xs. So this is a tangent vector on PGN, right? We have introduced explicit coordinate system, so there is no confusion about tangent vectors. This is the basis of tangent vectors. Okay. So take a circle C alpha on which the transition functions are of this kind. Zi equal to Fij, Zj and xs. Okay, I may not always write the x's, but it's understood. All the Fij's depends on x.
VSs are vector fields on the whole of the Riemann circles or
No.
just on the circle?
On the circles. Okay, so these are not globally defined vector fields. Okay, these vector fields are, that's why I didn't put any arguments here. Okay, these will vector fields only defined around the circles. Okay. So Vs will be defined as minus del f ij del xs so that now I can put the argument Vs of Zi on C alpha. Okay. Now it could also be that this particular circle is an overlap circle between a Zi and a WA. Okay? Because various circles. Some of them are overlaps between two Z's, some of them are overlaps between Z's and W's. Okay? So or we can also have Fia Zi and Fia of WA and X's. So it's in the first case it's this, in the second case it's minus del Fia del X's F inverse Ij. Now, one point to note is that unless we focus on some particular class of transition functions, in general now this vector field can have support on all the overlap circles because all the Fij's may depend on a single axis. For general parameterization, all the Fij's as well as all the Fis can depend on a single axis. Right? Okay, the parameterization that I used here I have chosen so that one particular Fia depends on the Q's, one particular Fia depends on the P's. Okay. So there, this Vs, for each case, Vs will have support only on one particular circle. Okay. But that's not necessary. Okay. In general, Vs may have support on all circles. Is clear?
Vector fields on circles.
Yes.
Can I just think that if I try to extend them over the Riemann surface, they may develop singularity?
They will, because if they don't develop singularity, right, that means that you can just remove them by reparameterization.
Yes.
Yes, so they will develop singularity typically.
Yes. So then I can, for each of such vector field of circle, I can think of them monomorphic systems of the corresponding bundle. Then the whole thing I can just think of a bunch of such sections.
Yeah, you can think of a bunch of such sections, but the different vector fields have no relation to each other. Right?
Yes.
That vector field defined on the first circle and the vector field defined on the second circle may not be analytic continuations of each other in any way.
Yeah.
Yeah. So each vector field has like a metamorphic section of some circle, but it may not even be metamorphic. Right? It may have their branch class poles. We are not saying anything. But on the circle, it can do various things. Okay, so right, the only demand is that the vector field should be well defined. When you are defining this on a particular C alpha, right, it's well defined in a band around that C alpha. Right? Because the transition functions are smooth. Right? So deformation of the transition function should be described as smooth vector field. But that smoothness is only required around the circle. Right? Away from the circle you don't care. Okay, now we define ds as integral ds times b plus integral ds bar times b.
So, can you please explain that part? When you say that these VSs are changing in such a way that it's done only around one circle and not that part?
Oh, because see, you look at this definition, right? Here I am saying that on any circle, so on every circle there is an overlap function, right? If that overlap function depends on excess, it's non-zero. Okay? So in general, each overlap function will depend on all the excess, right? So the Vs will be non-zero on each of these overlap circles. Okay? But if you parameterize in the way that I have done here, you look at it here, right? Now suppose you take xs equal to q alpha, right? When you take del del q alpha,
If I doesn't depend on Q.
yeah, only one of the Fi's will depend on q alpha, others don't depend on it. Then Vs will have support only on that side, right? But that's a special case; it's not necessary. Then you can introduce the coordinates in such a way that all the Fi's depend on all the x's. Okay, that's a general case. Okay, so this, what does it mean? It's a contour integral of b times bs, but this contour now runs over all the overlap circles. Okay? Now in special cases, when VS has support only one overlap circle, this control will run over only one overlap circle. Okay? But in general, this will run over all the overlap circles. Is this clear? Okay, so now we can define omega s. So definition, omega s, A1 to n. Omega s will always depend on these external states. Is ds1 to dsp product I equal to 1 to n ai. So these ai's have to be inserted in the particular coordinates, local coordinates, which depending on the point and region that you are calculating it in. Okay, and the sum over SIs are implied, of course. Repeated index, so sum over SIs. Implied.
So this is omega p, right?
This is omega p, yes, thank you.
So just one clarification about this notation.
Yeah.
Suppose you are looking at three punctured sphere.
Yes.
Okay. And overlap of that which say around the three punctured sphere. Then this Vs Zi,
Yeah.
that Zi belongs to one of the three punctured sphere coordinate or in general?
Well, it depends on, so there is Zi and Zj.
That
Right?
is it, Zi and Zi.
Yeah, so you can write Vs in terms of Zi or in terms of Zj.
That is it.
Okay, this integral will not depend on whether it's in terms of Zi or Zj. Okay? But when you are defining an overlap between Zi and Zj,
Yeah.
right, only those coordinates are relevant, right? Because on that circle,
Yeah.
right, you can either use Zi coordinate or the Zj coordinate.
Yeah. I was asking this question in context of you were saying that like this V could be defined on all circles. But
Yeah.
all circles pertaining to a given sphere, right?
All circles which are the overlap circles on which you have defined the transition functions. In order to define a Riemann surface,
Yeah, but given one of the Zi's, then you have probably defined the neighborhood of a particular circle, right?
well, not the neighborhood, I define the coordinates on the three-punctured sphere,
Yeah.
right?
So if I define Zi, then I have defined which three-punctured sphere I am looking at. Right?
Yes, exactly. Yeah. So in this,
Then this V would be defined only on one of those three circles, or maybe on all three.
no, there is only one circle here. See, there is suppose it's a three-punctured sphere, right? So there are two punctures over here, two punctures over here.
Yeah.
Okay. So around each puncture you cut out a disk. Okay. Here also. Okay. So we have four disks.
Yeah.
Okay, and two spheres.
Yes.
Right? So call this Z1, Z2,
Yeah.
and this is W1, W2, W3, W4.
Yeah. So suppose I define Vs of Z1,
Yes,
then it can have support only on those
On
three
this
circles.
only on this one. Because Vs of Z1, see,
But
So-
it depends upon whether it is capital F or small f, no?
yeah, so you introduce a coordinate Q, okay, in which you take the transition F1, 2, if you take Z1, 2, Z1 minus A1 equal to Q over Z1 minus A2, Z2 minus A2, okay?
Yeah.
Z1 is equal to W1
I see. Okay.
plus QW1.
Okay, so I can invert the relation between Z2 and write it on the other circle.
No, you don't invert anything. On each circle you specify a Okay, on each circle you specify a transition function. So Z2. So on this circle, okay, you will specify the relation between Z2 and W3, right? So Z2 equal to A2 plus I am using, let's call it A1. Okay. So A1 I have used up. So A2 plus Q square W3. A2 plus W3. A2 plus W3. Z1 equal to A2 plus W2. Here it should be A2 plus W3. A2 plus W1, A2 plus W2 plus 2Q W2. Okay. Here it could be A2 plus W3 plus Q square W3 and Z2 equal to A3 plus
A2 plus W4.
So A2 I have already used up. So A3. See, this is A1, A2, A3, right? I am using three concepts. Here also A1, A2, A3. Sorry, A1, A2, A3. Okay. So A3 plus W4 plus 2Q square W4. Okay. I can choose one parameter as in this way. Right? In which case all the overlap functions, the VS will have support on all of these. Right? Because the LDLQ of the transition functions is non-zero on this, as well as on this. Is that clear?
Yeah.
So it depends on where you introduce your coordinates on the model.
Yes. So even if I write Vs of Z1,
Yes. So Vs has to be defined for each circle independently.
yeah,
Right?
exactly.
So on this circle, Vs of Z1 will be determined by this overlap. Only by this. It doesn't care about what these are. Right? You could have written Vs of Z2 on this circle.
Yeah.
Okay, and integrated over Z2, but that gives the same result.
Yeah.
Okay, because it's from the same transition function. You just invert it.
And del derivative with respect to Q is non-zero everywhere. So all of them would have.
Yeah, so now there will be integrals of B. So in defining Bs, for example, you have to involve integrals over this, and this. Okay. So in general, you can make life very complicated, right? Because you can introduce these excesses in such a way that it appears everywhere, right? Each excess appears in all the transition functions. Okay. But in practice, of course, you want to make life as simple as possible, right? So you could choose that way, the way I described. If you choose it that way, right, then each del excess, okay, gives you a Vs that has support only on one circle.
So these sort of VSs, I can just think of basis vectors and
Exactly, that's right. These different choices are just different ways of coordinating the model space, right? The coordinates in PGN. Is this clear?
What are these points A2 and all these things? Because when you're gluing this circle,
Yes,
the circle on one side of Z1 and Z2, that the middle circle.
that's right.
So you're using these A1 and A2, but the A1 and A2 are not any physical points. Right?
No, you just make them anything. That's all right. 0 or 2 you can choose. Right? This is just to give the relation. Okay? It only says that you are cutting out some region around A2. Right? I mean, in the way that I have specified overlap circle, A2 would have been the position of the function. Right? Because W3 equal to 0 is the position of the function. Okay, but this is completely arbitrary. I mean, A1, A2, A3 are just arbitrary points. If you change A1, A2, A3, keeping the Q's fixed, you go to a different quantum model space, right? So you could use A1, A2, A3 also as parameters. Okay? Is that you have to think of A1, A2, A3 as something given, 0, 1, 2, okay, and introduce the parameters elsewhere, like in the Q's that we described.
So this infinite sum, what happened to it? This
What? So infinite sum is there because this Bs, so what did I define here? This sum over S1 is an infinite sum. Right? The number of circles, each Bs gets support on finite number of circles because there are only finite number of overlap circles, right? But each such overlap function depends on infinite number of parameters. Could depend on infinite number of parameters.
But in this example, Zi minus m, where is this? You have BM.
Oh, no. In this example, I have not introduced the other coordinates. This is not a full coordinates of PGN. Right? These are only the coordinates of the MGN that have described, the Q. Right? But to introduce a full set of coordinates, I would have to put arbitrary transition functions here.
So now your coordinate is only sigma gm, not the fiber also.
Yeah, or a section. Because I have chosen a specific choice, made a specific choice of local coordinates on the surface.
So still not the fiber. Fiber is not considered.
No, so in this example, the fiber is not there.
Because they are only Qs.
Well, fiber is not there, or as I said, you can think of this as I have chosen a specific section. Right? And I am defining the omega on that section.
Because Qs only needed for this sigma.
Exactly.
So this way of parameterizing that you specify a Green fixture on these sphere parts, this naturally decouples these coordinates on modular space and the other one.
Yeah.
Is this some general property valid on arbitrarily?
No, I just gave some example. Right? It's of course a general property. Locally you can always do that. Right? Because I am not asking anything about the Riemann surface. Right? At any generic quantum Riemann surface you can do this. Okay? But in practice this is not something that you have to do. Right? This is just a formal definition of B. I'll describe how you use it. Right? In order to use it, you don't have to always work with infinite number of coordinates on the on PGN. Right? Because then it like becomes hard. But this is the formal definition of what the omega means. Is this clear?
So finally, the integral will be over the dx's as well.
Yes. Finally, the integration is going to be over the dx. Not as well. This is the only integral that you have to do, right? Because ultimately, when you are integrating over a section, you have to integrate over the coordinates of PGN, right? Which are provided by the dx's.
But earlier, the coordinates used to be in this another kind of. They were like Q's and all these things, and they were the coordinates on MGN.
Well, that's when you level section, right? This here I am describing that if you take an arbitrary p-dimensional subspace, how to integrate, right? Once you choose a particular section, yes, ultimately what are you supposed to do? You take this omega p and you restrict it to a section, right? And you integrate over those, right? And then the integral will reduce to the coordinates that level the section. Okay, and I'll describe next how to do that, because that's in practical terms that's what you need to do, right? But for formal identities, you think of this as a P form on PGN, right? And then any identity you have to derive on this, you will hold when you restrict to any section, right? So while proving identities, you don't restrict to any particular section, you just think of this as a P form on PGN. Are there any further questions on this? Okay, now I'll just rewrite this in a slightly different way. Okay, which is not necessary now, but it will be a useful notion for dealing with superstrings. So this I'll write omega p A1 to An as OP. Okay? Well, OP is a formal object which is ds1 dx s1 h ds2 dx s2. Okay, that's a formal way of writing it. Okay, but what you mean by this is what you have here. Okay, but this formal symbol will be useful in writing formula in a simple way. Okay. And I'll also introduce another symbol, omega, It is sum over 2 omega. This is and O, it is sum over 2 omega. Okay, it just takes values. Omega, for example, is not a form of a definite degree. Right? It takes value in a vector space where you have combined forms of different degree. Okay, similarly for O. Okay, it's just a formal notation.
Here the sum means direct sum of vector space.
Direct sum of vector space, exactly. I mean, you don't add anything, right? What you mean by this is omega 0 plus omega 1 plus omega 2, etc. Okay, but it's useful concept in the following sense that if you take omega with omega tilde, okay, that can also be thought of as a formal sum like this. Okay, it's sum over p q omega p with omega q omega tilde. Right? That's the definition of omega with omega tilde. Okay. And now, if you pick an R form from here, right, that basically means that you pick all the R forms from this product. Okay, that's the way we are going to make use of this. Right? So, just the same symbolic way of writing the sum. Okay, once you have written it this way, okay, then if I write omega with omega tilde R, that basically means that it's the R form of this. Okay, only p plus q equal to R it contributes, otherwise it doesn't. Okay, if this bothers you, don't worry because this is just a symbol. Okay, when I write a similar formula for superstrings, okay, I am going to use this notation. Okay, and then I will try to explain again what it means.
Also, suppose I try to contract this omega
Yes.
with say R vectors.
No, this omega you don't contract with anything.
Okay.
This omega you just think of this as a formal omega only after you have gotten some p form out of it, out of some manipulation.
Okay.
They will think of contracting. Right? So, as I said, this omega you just think of the formal symbol. Okay? The only utility of this is that it allows you to define objects like this. Okay? The omega with omega tilde will mean that's a formal sum like this. Okay? But, and that again is only formal. But now if you say that it's the rth degree form of this, right, that means that you pick all the terms from here which are degree r. Right? Which means omega 0 is omega tilde r, omega 1 is omega tilde r minus 1, omega 2 is omega tilde r minus 2 and so on. Right? So that's the simplification that we are going to use. Right? Now when you have two products, of course it doesn't, I mean you might as well have written like this. Right? But you will have multiple products like this. Right? And that's why this symbol is useful.
This angular bracket still denotes over sigma gn. This
Sigma, yeah, sigma gn. All of these will be sigma gn. Okay, so this is a formal definition. Okay, it is useful. This definition is useful to prove various identities. But when you actually need to use it, okay, you don't need to define infinite number of coordinates because eventually, whenever you make use of omega p, you integrate it over a subspace, and that's always a p-dimensional subspace. Right? Omega p can only be integrated over a p-dimensional subspace. Okay? So what I will describe now, okay, is something that is more useful in practical terms. Okay? That imagine that you have a p-dimensional subspace of omega of pgn. Okay? Then you want to know how to project omega p on that p-dimensional subspace. Then instead of having some general omega p which has its legs on infinite number of directions, then you want to sort of project it on a p-dimensional subspace.
So that is raised to the property of tilde.
What?
So omega p raised to omega tilde q raised to the power.
No, get that. Yeah. This is from the previous. how to compute restriction of omega p on a three-dimensional subspace of PGN. Okay? Any p-dimensional subspace. Okay, at this stage you don't care about whether it's a section or not. Okay, take some p-dimensional subspace of PGN. Now, what does it mean to give a p-dimensional subspace of PGN? It means that we have some intrinsic parameters, okay, that level the p-dimensional subspace, p intrinsic parameters, y1 to yp are the coordinates on the subspace, coordinates level in the subspace. And a given point in this space is a point in PGN. Right? A point in PGN means the set of transition functions Fij and small fi. Right? Because that's what defines the point in PGN. Right? That defines the point in MGN as well as the phi. Okay? So, given a subspace of PGN is equivalent to saying that we have the Fij's as a function of y's. And similarly, the relationship between the z and w that's what gives the subspace of PGN. Right? Because what you are doing is that for every y1 to yp, every point in the y space, you are giving a point on PGN. Right? And as you vary over y, you get a p-dimensional subspace of PGN. Now you have finite number of parameters. And you have to define omega p on this subspace.
The earlier equation that you have written to give that example, that was just one dimensional.
Yes, that was one dimension, two dimensional because q was a complex parameter. Right? That is a two-dimensional subspace, exactly. So that for that example that was given that q, right? So I introduced one parameter q to level all the transition functions, right? That was like a two-dimensional subspace of M04 or P04 that was describing. Right? So that's why I was thinking think of more this as a section rather than a parameter as an MGN, because I am giving also the choice of local coordinates. Right? In that example, I gave the choice of local coordinates because I gave the relationship between z's and w's also. Right? So it was more like a two-dimensional subspace of P04, okay, which is a section. Okay, so now we have to define omega on this subspace, omega p on this subspace. Okay, and the answer is very simple. So omega p on this subspace is obtained following previous description with x replaced by y. Okay, whatever you did with x, you just do with y. Okay, but now y has only there are only p y's. Okay, so this actually tells you how not only how to restrict omega p on this subspace, it tells you how to restrict all omega q's for q less than or equal to p. Right? Because we cannot have a omega q with q larger than p because there are only p coordinates, right? Okay, and this is related to the fact that if you have a p form on this big manifold PGN, its restriction to a q dimensional subspace is 0 if q is less than p. Say, take a 2 form, okay? On a one dimensional subspace, right? What we mean by restriction of a 2 form on a one dimensional subspace is 0. Okay? A 0 form and a 1 form can be defined on a one dimensional subspace. Okay, but 2 form cannot be defined on a one dimensional subspace, you just declare it to be 0. 2 form restricted to a one dimensional subspace is by definition 0 because it doesn't have the one of the legs. Okay? If it's dx1 or it's dx2, right? The dx2 leg is not available, right? There is only one dimensional subspace. Okay. So if you do it in component notation, okay, if you do it in component notation, then what we are doing is following. So subspace Y of PGN corresponds to giving xi's as some function of the y's. X's, like I call it x's. Right? All the x's are specified by some functions of y's. Okay, a p-dimensional subspace. Now suppose I have a q form. Suppose I have omega q. Okay, which is omega q s1 to s2 dx s1 okay. Now what do you mean by restricting omega q to the subspace? What do you mean by this is the following: omega q s1 to s2 each dx is replaced by in terms of dy, right? So each dx is write as del phi s1 del y alpha dy alpha with del phi s2 del y alpha 2 dy alpha 2 and so on. Yeah, this is what we mean by restricting omega q to the subspace y. But from this it's clear that if q is larger than p, sorry, this is q, right? This is because we have q form. Then if q is larger than p, then this is 0. Yeah, there are only p y's, right? This dy alpha 1 to dy alpha p is totally antisymmetrized in the index alpha 1 to alpha q. Okay, so there is no way you can get a non-zero result. Right? So this is 0 for q larger than or equal to p. So this is 0 for q larger than p, but non-zero for q less than or equal to p. Okay? It's well defined for q less than or equal to p. And what this procedure is calculating is precisely this. Okay, precisely this restriction. Okay, but I want to emphasize that to calculate this, we don't have to go, we don't have to first define omega in terms of infinite number of coordinates and then do this contraction, right? You can do it at one go. Just think of the transition functions as functions of a finite number of coordinates, and then whatever you do with x, you do with y. Is this one clear? Okay, now let's try to go back to the identity. We said that omega p of sum of what I equal to 1 to n p di on A1 to n is minus 1 to the p d omega e minus 1 and this is the identity which we tried to motivate last time. But I'll not again derive this, but let me just again make it clear what these sides mean. So this side is clear, right? This is omega p has been defined as a p form. Okay, we are just taking d of that. This can be defined on this infinite dimensional space. But if you are not happy working with infinite dimensional space, you can work any subspace of MGN or PGN, and this is still valid. Right? This, I mean, once this equation is valid on the full PGN, it is also valid when you restrict both sides on any subspace. Now let's see what this means. Okay, so omega p of this means what? Okay, what it means is the following. This means it's dx1 dxs1. See, I am writing the dxs1 inside, but you can of course pull it outside. Right? These are just formal differentials which are nothing to do with the conformal feature correlation function. Right? These are the differentials in the formula space. But it's convenient to have writing this. So if we didn't have this, then we just had the product over I. Now, what we have is integral jd of z dz plus integral jd of z dot dz dot product over I. That's the meaning of the right hand side, of the left hand side. Okay. Last time we wrote some signs, minus 1 to the NAI and so on, but that's because if you want to move this through the AIs, right, you just become a minus sign because of the anti-convolution properties. Right? This is Grassmann order. So any Grassmann order AI, when you try to move the position, you just become a minus sign. And this contour, as I told you, has to be around every function. Something like this. Okay, it goes anti-clockwise around the function. And the way one proves this identity is that basically you pull this, this is QB, right? The contour integrals are around every function. You pull it on the A1 surface, okay, contract the contour to a point, and in that process you pick up the commutators, anti-commutators from these objects. Right? You pick the anti-commutators one at a time. Right? So it's a sum of terms. In each term, one of the D gets converted to T. Okay? So you insert then TSP rather than DXP, right? You integrate V of V times T rather than V times B. Okay? And insertions of integral V times T, okay, is essentially del del XSP. Okay? That's the derivative of this object. If you replace DSP by TSP, okay, that gives you del del XP of this. Right? That's the origin of this relation, right? Because that's why you get this D. Is this clear? Okay, I'll try to work this out in the specific example of 4 punctures here. Okay, but this is a general reasoning, okay, that leads to this general result. Now what about this minus 1 to the p? Right? Where is this coming from? Okay, it's just a simple sign coming from the fact that on this side, right, you see, each time you pass it through a b, you pick up a minus sign. Right? Because b is dash 1 odd, q is dash 1 odd, right? So here you are picking up minus signs as you go. I mean, this one, for example, will have no minus sign, the next one will have one minus sign, the next one will have no minus sign. On the other hand, b is acting from this side. Right? When you calculate d omega p, right? D is acting from this side. Okay? And hence, that so is here, for example, when you put del xsp or tsp, right? tsp is inserted here. The number of signs you pick up depends on how far it is from that side. Okay? Whereas when you put del xp, right, you want to put a dxsp here, right? Then it depends on where you want to put it from the left. Okay, and that mismatch basically is giving rise to this minus 1 to the p. Okay, so it's a simple, argument involving where the operator is acting from. Okay, you could have, tried to get around this minus 1 to the p if you had defined the b's so that b's come in the opposite order as the dx's. And if you have taken dxs1 or dxs2 or dxsp and inserted the b's as dsp minus 1 up to ds1, right, then this problem will not be there. Right? Because then you will first hit ds1, right? And the d on this side will again have del xs1 first. Okay, so you could avoid this minus 1 to the p, which basically means that instead of defining omega p in the way you have defined, right, you put an additional minus sign, an additional sign factor in the definition of omega p, right, which can get rid of this minus 1 to the p. Okay, well, we will define it this way and we will work with this minus 1 to the p. Is this clear? Okay, this is not a proof, this is just a way to motivate where this relation comes from. Okay, there are detailed proofs, right? But I will not try to do this. I will try to see how to make use of it. Okay, and I will see how this works in a given example. So one application of this we have already seen yesterday, right? That application was if A1 to An are physical states, then integral, okay, over a section is independent of which section you choose, okay, up to boundary terms. Okay, the boundary terms have to be checked separately whether they vanish or not. Okay, but up to boundary terms, the integral of omega over a given section is the same when you integrate over a section. Today I will try to give another application, application 2. And that is decoupling of pure gauge states. So suppose A1 equal to QB lambda 1 and QB AI equal to 0 for I greater than or equal to 2. Of course, QBI is 0 also for I equal to 1, okay, because QB square is 0. Okay. For us, QB will always be QB plus QB part, right? Both holomorphic and anti-holomorphic part. This operator. Then let's see what we can do about this. Then we can make use of this identity to conclude that omega p of QB lambda 1 is given by minus 1 to the Okay, what have we done? We have applied this relation, but A1 replaced by lambda 1. A1 up to n are arbitrary states, right? Replace A1 by lambda 1. Okay? Then the left hand side we get a one term QB on A1, the others are A2, A3, etc. There are of course other terms on the left hand side, lambda 1, QB, A2, and so on, but those all vanish because of this relation. Yeah, so left hand side, so this is the left hand side with A1 replaced by lambda 1. So on the right hand side also I have replaced A1 by lambda 1. Is this clear? Not clear. It's just direct application of this identity, right? With A1 replaced by lambda 1. Now suppose Qgn, Mgn, and then something. And you want to calculate integral over S of omega 6g minus 6 plus 2n of QB lambda 1 A2 to n. So this is an amplitude. This is our own shell amplitude because all are BRC invariant. But one of these is actually our BRC trivial. And it's QB lambda 1. So now using this identity, 6g minus 6 plus 2n is even. So using this identity, we say that this is integral s d omega 6g minus 6 plus 2n minus 1.
So does QB act like derivatives?
Yes, roughly you can, that's what this identity shows, right? That when you apply sum over QBI on all the operands inside, right, that gets translated to a derivative on the Qgn. Right? So in that sense, yes, QB acts as derivatives.
So here also, I think the QB is acting only on lambda 1, but then I think if we use the identity that QB acting on lambda 1 into an and then the other
No,
identity.
here QB is acting on lambda 1, but the other terms are all 0. See, suppose you have sum over QBI, right? So this is equal to omega p of sum over QBI lambda 1 a to 2n. Okay, why? Because this means all omega p QB lambda 1 a2 up to n, that's the first term. Then there will be omega p of with a minus sign lambda 1 QB a2 a3 and so on, but QB a2 is 0. Right, by this identity. So what I have written on the left hand side of this equation is the same as what appeared on the left hand side of that equation. Right? Is that because A2, A3 up to n are all BRST invariant, that is identical 0. Right? Otherwise, it's exactly the same identity that we had there. Okay? The reason that there is only one term is because of this identity. So this we again see is a total derivative integrated over S. So this is as boundary terms. Okay, in fact it also says what boundary term it is. This is the integral over the boundary of S of omega 6g minus 6 plus 2n minus 1. Yeah, by again Stokes theorem. Integral d omega on the surface. There S is the boundary of S. That integral of omega on S is integral of b omega on s is the same as integral of omega on the boundary of s. So then you have to go back and check separately if the integral over the boundary vanishes or not. Okay. Now I should also tell you that there are many identities of this kind. Okay, where you want to prove some identity, you should it's a total derivative in the total derivative and hence integrate to boundary terms. Okay. But sometimes you may find the boundary terms are non-zero. Okay, and those are physical interpretation. Okay, for example, sometimes the symmetry may be spontaneously broken, okay, and that will show up in this analysis as non-vanishing of the boundary terms. Okay, if I have time, I'll discuss later a specific example of supersymmetry breaking, right, where you will see that the naive word identities fail, right, precisely because there are boundary terms, okay, which are non-zero. Okay. Most cases, the boundary terms vanish, okay, and hence you can conclude that the usual word identity is hold.
You're talking about worksheet symmetries or space-time?
These are all space-time symmetry because these are space-time based transformations, right? Because you are adding QB lambda to A, right? That means you are in terms of if A was the Bardakh order for electromagnetic field, right? Adding QB lambda to it corresponds to changing its polarization by KB. So that's a space-time symmetry.
How would the boundary of the moduli space know space-time symmetry is broken?
Because boundary of moduli space, as we saw, right, you can think of this as coming from the k equal to 0 end, right? I mean, the way we sort of dealing with boundary of the moduli space, we just broke up the integral. Near the boundary, it's always you give a field theory interpretation, right? And spontaneous symmetry breaking is always an infrared effect, right? The zero momentum component of phi gets vacuum expressed in that. That's why spontaneous symmetry breaking takes place, right? So the boundary terms capture the infrared effects, and that's why the spontaneous symmetry breaking can take place. Okay? But as I said, in most cases, the boundary terms will vanish. Okay, and you have the usual realization of the word identities.
Also, there is the factor of -1 raised to p.
Oh, but it's, in this case, p is even.
Okay.
Right? It's 6z minus 6 plus 2n. You have to write in minus 1. Is this here? Okay, let's see if I can do the example quickly. Okay, so we want to illustrate.
So such symmetry breakings are always spontaneous sort of symmetry breaking.
Yeah, because it was there to begin with.
So it's not, it will never represent a situation where you have a classical symmetry and it becomes anomalous. Not that sort of.
Well, the anomalous theory, I mean, when a gauge symmetry is broken, anomalously, right? That's an inconsistency of the theory itself. Then the string theory itself is not well defined.
Yes.
Right? I am assuming here that the string theory is well defined. Right? See, anomalous symmetries typically are reflected in the lack of moderate invariance. Right? Those are also in some sense boundary terms, but they are not boundary terms of the kind we are talking about here. They basically mean that when you restrict to fundamental domain, right? You have to make sure that the contribution from here and here are the same, right? Otherwise, you cannot restrict to fundamental domain, right? So, but if the theory is anomalous, right, then you will find that the integral doesn't have modular symmetry. Okay, so that will also show up as some kind of boundary term, but those are the boundary terms coming from the boundary of the fundamental domain. Right? The modular transformation relates, for example, this part to this part. Right? If the integral doesn't have the same value at these 2 points, then it doesn't matter. Mean much to say that you will integrate over the fundamental domain. Right? Because the integral doesn't have the symmetry of that allows you to go to the fundamental domain. Right? So you can think of this as a boundary term, but those are the boundary terms that we are talking about here are the ones that are coming from the infrared. Okay, not boundary terms of this kind. You are assuming that the theory string theory that we are dealing with is already modular independent and consistent. Okay. So there are some anomalous gauge symmetries. Okay, so I'll just give the steps and then I'll leave the working out to you. Okay. So what we want to do is we have taken 4 punctures here, okay, but we don't want to work on the whole of P04. That's infinite dimensional space, right? We'll pick a section, okay, and show that restriction of this relation, or that general relation that we wrote down, to the section, okay, which is a 2-dimensional subspace labeled by one complex parameter, okay, the identities only. Okay. So in fact we will simplify it even further. Okay. So take 4 states. A1, okay, which I will call QB lambda 1, which I will take to QB lambda 1. A2, A3, A4. Such that QB AI equal to 0 for I equal to 2, 3, 4. Okay, because I am just going to illustrate how this works, right? I am not trying to give a general proof. Okay, but this will give an idea of what this means. Okay. So what we want to show is that omega 2 UB lambda 1 A2, A3, A4 equal to B omega 1 lambda 1 A2, A3, A4 on any section. Okay, let's at least try to see how this works. Okay, this is a very special case of the general identity. The section that I am going to choose is the one that is occupied by gluing 2 3-punctured spheres. So you put A1, A2 on this sphere, A3, A4 on this sphere. Okay. Choose specific local coordinates. Okay, we don't care what it is. Okay. Just choose some specific local coordinates on A1, A2, A3, A4. And then glue the 2 spheres by the boundary fixture. Okay. So we introduce the local coordinates. So A1, let's say that W1 is the coordinate system here. Here is W1 2. Here the constant that would have been there. Okay, initially being the boundary fixture. Here it was W1 3. This is W2 1, W2 2, and this will have been W2 3. Okay, and you glue by W1 3, W2 3 equal to 3. Now, if you recall, we actually constructed the omega 2 on this. Okay, in terms of the surface state circle. So, let me just remind you what they were. Okay. So, introduce sigma 1 and sigma 2 by the following relation. Sigma 1 5 is by definition A1, A2, 5 on the first surface. Okay, these are inserted by the corresponding local coordinates W11, W12, W13. Similarly, sigma 2 phi by definition is A3 A4 and sigma 2. I'll also introduce sigma 1 tilde. Okay, sigma 1 tilde phi will be lambda 1 A2 phi and sigma 1. Okay, same local coordinates. State has been replaced A1 by lambda 1. Now there is a relationship between sigma 1 and sigma 1 tilde. So let's try to work this out. Okay. So sigma 1 phi is QB lambda 1 A2 phi. Right, because A1 is QB lambda 1. This is the integral of the BRST phi around lambda 1. Now you can give three punctures here. QB was being integrated around the first puncture where lambda 1 is inserted. You just deform the contour and try to shrink it to a point. In that process, it will pass through A2 because A2 is BRST invariant. Okay. But it will hit. So the claim is that this is lambda 1 A2 phi, QB phi. Okay, I should have said something more. We take AIs to be host number 2 and lambda 1 to be host number 1. Okay, I could have worked with other host number, but again, let's be very specific. So in doing this, okay, in getting this, there are two minus signs which are cancelled. Okay, the first minus sign is that we have to take the BRST contour as clockwise around the first puncture, right? When you deform it and put it on the other punctures, it becomes anti-clockwise, right? So there is an extra minus sign because the anti-clockwise contour has to be reinterpreted as a clockwise contour. Okay. The other minus sign comes because the QB position has been shifted. Right? That's just a pure sign convention because in the Grassmann variable, lambda 1 is Grassmann odd. Right? QB was to begin with kept on the left of lambda 1, now it has been put on the right of lambda 1. Right? This is just a trivial sign. Okay, but we have to follow the convention, right? Sign, the sign depends on where QB is placed. So those two minus signs are cancelled. But this one, by definition, is sigma 1 tilde phi. Sorry, sigma 1 tilde QB phi. Okay? Look at the definition of sigma 1. For any state phi, it is this. Okay? So here, phi has been replaced by QB phi, so this is sigma 1 tilde QB phi. So this tells us that sigma 1 is sigma 1 tilde QB. Is clear? Now let's calculate omega 2. Omega 2, A1, A2, A3, A4, and this is where I have to use the result that we had derived earlier. This, if you recall, is sigma 1 B naught bar into the L naught U bar to the L naught bar sigma 2. Oh, there is one more identity I need. and that's the following. Suppose you try to calculate sigma 2 with QB sign. Can you see what the result will be? I is replaced by QB sign. Right? That QB contour now can be deformed and put on F3 and F4. But F3 and F4 have been assumed to be RC invariant. Right? So this is 0 for every sign. Okay? This means that sigma 2 QB is 0. Okay, so now you see this is sigma 1 tilde QB. I forgot something important. Okay, there is this is multiplied. There is a dq by q with dq bar over q bar. Right? So you have to remember this. Right? In subtractive form, right? You have to put the dq by q and dq bar by q bar. This is what we have derived earlier. So what we can do is that we just take this QB and pass it onto sigma 2. Right? It annihilates sigma 2 by this relation over here. Right? If it annihilates from the right, it will also annihilate from the right. Just conjugate of it. You will get conjugate of this. So QB will annihilate sigma 2, but in that process it will commute to the L0 and L0 part. Okay? But it will pick up the anti-commutator from B0 and B0 part. Right? Those are L0 and L0 part. So this gives you omega 2 A1 A2 A3 A4 as sigma 1 tilde by what I does L0 B0 part minus B0 L0 bar, U to the L0, Q bar to the L0 bar, sigma 2, dq by q, L0 dq bar over q bar. Okay? This was the left hand side. Now let's look at the right hand side, okay, which I have erased unfortunately, but I like to do again. So right hand side, you are supposed to calculate omega 1 of lambda 1 A2 A3 A4. Because d omega 1. Because omega 2 of this is supposed to be d omega 1 of this, because A1 is QB lambda 1. Right? All the others are the same. So this is D, okay, and now I have to remind you what omega 1 was. Omega 1 is to be defined exactly in the same way. Okay? And if you follow exactly the same definition, what you will find is the following. It is sigma 1 tilde B0 into the L0, L0. But logic is exactly identical to what he did for omega 2. Okay, what have I done? I mean, I have basically used similar formula. Okay. Sigma 1 is replaced by sigma 1 tilde because instead of the state A1, we have the state lambda 1. Yeah, sigma 1 tilde was defined the same way as sigma with A1 replaced by lambda 1, right? That's why you have got sigma 1 tilde here. Here instead of B0, B0 bar, right? Where did B0, B0 bar came from, right? Because you are constructing a 2 form, right? So there is a dq is dq bar and dq gave the B0 and dq bar gave the B0 bar. Right? If you follow the same logic, now instead we are looking for a 1 form. Right? So you have a dq by q multiplied by B0 and add it to it, dq bar by q bar added to B0 bar. Right? Exactly the same logic that we used for letting omega 2. And now I'll revise the exercise to show that this is the same as this. Okay, let's see. When this acts on this, right? When this acts on this, what does it do? Q dependence. See, you cannot put a dq. There is no dq bar, right, on this because dq bar is already present here. Right? That will give us 0. So you just basically have to define the response to del del q. Right? Del del q will bring down an L0 over q part. Right? Del del q of q to the L0 is L0 over q multiplied by sine, right? That gives you dq by q as we have here, and it brings down an L0 factor. Okay, that's the first term when d acts on this. When d acts on this, you have to pick the del del q bar term. Okay, del del q bar will bring down an L0 bar over q bar and dq bar over q bar. But the dq bar over q bar has to be placed on the right? So in the process of taking it to the right, you pick up a minus sign, and that's this is a minus sign between these two. Okay, so from here you can see that this the origin of the minus sign, right? Because here the minus sign is coming because qb as it keeps passing through the b's, every time it picks up a minus sign. Okay? Here the minus sign is coming because the d when it passes through the other differentials it picks up a minus sign. Okay, so all the minus signs match except that q acts from the right, this acts from the left, and that's why this minus 1 to the p. Right? We didn't see that minus 1 to the p here, the p is even. Okay, but if you work things carefully, you will see that minus 1 to the p. Okay? So this is just an illustration of how this identity works. Okay? This identity is completely general, it's proved in a completely general terms. But this is just a specific illustration of how the identity works here.
But here it is only over part of the section. I mean, the surface bit took. I mean, it only covers the part of.
That's right. So you always prove things over patches, right? See, it covered part of the section if you restrict your q to be less than 1, and you can in principle continue q to be beyond 1, right? And by that process, you may be able to cover the whole section. Okay. See, when we did this analysis, we had a specific goal that we will keep the infrared part treat this as a field theory, right? And that's why we restricted q to be in fact less than e to the minus s naught, right? To get q to the e to the minus s minus I theta and to s from s naught to infinity, right? But that is only because you wanted to reinterpret this as field theory diagrams, right? But if you are just interested in seeing how to parameterize a section, okay, you could in principle take q to be anything. Okay. But nevertheless, I mean, it is true that this analysis is showing that locally how it works. Right? In different patterns, you may choose different coordinates, and every time it works this way. Yeah, this is not even proving this identity in general, right? We have not taken an arbitrary subspace of PGN. Right? We have taken a specific section of PGN or a specific class of sections because we didn't make any commitment about what the local coordinates at A1, A2, A3, A4 were. Right? Those are still arbitrary, so it's valid for the white class of sections of PGN, of P04. So I think I'll stop here and continue tomorrow. So tomorrow I'll start superstrings. Okay, and there you will see that all these omegas will be important. So in case you have confusion about omegas, you should ask tomorrow before I start the lecture. Because I mean, these are not essential for bosonic strings, okay, because you can get by in bosonic string without just using this omega 2g minus or 6g minus 6 plus 2n, right? This one form you introduce for every genus and every n, right? And you never have to worry about section because you can always go, I mean, unless you are interested in offshell amplitudes. Okay? If you want to on-shell amplitudes, you just think of you will worry about TGN, right? You always think what will be MGN. But you will see that in superstrings, you have to generalize, right? And there are all the omegas are involved.
Tomorrow same time?
Yeah, tomorrow will start the session.